Y, and over here, this is our rotation about Z. Okay. So first of all, we have to determine our equivalent load on the distributed load. So this is our equivalent load. And this is equal to 50 times 10 to the power 3 multiply by 3.2. So our evenly distributed load, 50 power 3, is equal to 160. Okay. So our equivalent load is at 160 times 10 to the power 3. The position of the equivalent load, so this is equal to 1.6. And sort out all your distance first. There's a lot of information down here, but you have to sort out all your distance first. And the distance from here to here is 2.4 plus 0.8 plus 0.8 minus 1.6, 2.4. Okay. So these are our distance. Okay. Sort out your distance first. Make your life easy. Okay. Or not, you can get lost. So now we're going to take moment about point D. This is where we're going to take our moment. Okay. So we have by minus by minus 2.4, 3.2, and plus by 160 times 10 to the power 3 multiplied by 2.4. The whole thing is equal to 0. With this, we can compute by. So this is equal to 160 times 10 to the power 3 multiplied by 2.4 divided by 3.2. So the reaction at B is 120 times 10 to the power 3 Newton, and it's going up. Okay, so this value is important to us. Next, we do summation about forces in the y direction is equal to 0. And this will be equal to by 120 minus by 160 plus by dy is equal to 0. dy is equal to 40 times 10 to the power 3 Newton. From here, once we know these two values, we can sketch our shear force and bending moment diagram. Okay, so I'm going to align this with the positions. Bear with me. So this is our point A. Then next comes to our point B. Then we have our point C. And finally, we have our point D. Okay. So that's where we are going to sketch and label our shear force and bending moment diagram. Okay. So I'm going to have our x-axis. Wait, nothing is working. Wait, hold on. I think it's my computer. Some of you should say, yeah, it's you, Eugene. Yes, ma'am. No, I'm just doing this so you can learn better. Okay, you don't need to do like me. Okay, I'm just teaching down here. You don't need to draw like this, but I want you all to see things better. You get what I mean? Right. So this is our x. This is our v. 0, 0.8. Oh, let me do 0.8 properly. 0.8 3.2, 4.0, okay? Then I'm going to label this 20, 40, 60, 80, 100, 120, and then this will be equal to minus 20, minus 40, minus 60, and I'll stop at minus 80, okay? So at point A is equal to 0, right? Then at 0.8, right, is equal to what? So at 0.8, so 0.8 times by what? Times by 50 is equal to 40. Okay, so it'll come down here. So this, we get this by 0.8 multiplied by 80. So this is equal to 40 times 10 to the power 3 Newton. Okay, so this is all times 10 to the power 3 Newton. Okay. Any idea? Is it a curve or a straight line? Why? So it's linear. Okay, so it's linear. So we know that over here we have 40 times 10 to the power 3, right? Now this is 0.8 times by 80. Why is it 0.8 times by 80? I'm going to do some things to help you recall. So if we were to look at 0, okay, so we're going to form the shear force and bending moment equation. Okay, so we're going to form, okay, shear force and bending moment equation, right? So we know that over here, so what I'm going to do, I'm just going to form from 0, just help you recall what you learned in 2P. Some of you have done 2P long time ago. Some of you have just done last term. We are going to have a limit from 0x to 0.8 meter. So when we have a section, this is our point A. The distance from here to here is x. We're going to assume positive shear, and we're going to assume what? Positive bending moment. And this over here is equal to what? Is equal to x, or is equal to 50 times 10 to the power 3 multiplied by x. The distance from here to here is equal to what? X over 2, right? So from here, when you do static analysis, summation of forces equal to y is equal to 0. You have what? 50, you have minus 50 times 10 to the power 3x minus v as a function of x is equal to 0. V as a function of x is equal to what? Minus 50 times 10 to the power 3x. Okay. The fact that it's negative down here, that's why your slope is what? Your slope is negative. Okay, so if you now substitute x is equal to 0.8, v at 0.8 is equal to minus 50 times 10 to the power 3 multiplied by 0.8 is equal to minus what? 50 power 3 times 0.8 is equal to minus 40 times 10 to the power 3. So that is the physics and mathematical expression. Are we clear? Okay, so if some of you don't see that, now you see that. Okay. Now at point B, we are going to push it up by what? B what? 120. So push it. So over here, this is our next point. How we get our next point is 120 times 10 to the power minus 3. Times 10 to the power minus 3. Right, you did. minus by 80 times 10 to the power 3. So at this point is equal to what? Okay, 40. Come on, you did. So at this point is equal to what? 80 times 10 to the power 3. So from here, we draw our next line. We draw it back up. Okay. And then if we look at dy is 40. So it has to start from minus 40, right? So it comes down here, right? At 3.2, there's no forces. You draw a straight line. And now the next thing comes, you draw a straight line connecting one end to the other end. So this is how you construct your shear force diagram. Are we clear? Okay, very straightforward. I'm going to move this up. Now, with the shear force diagram, we still don't know, like, if okay, not we still don't know. I correct my statement. We still don't know. Okay, I'm going to correct my statement that we still don't know. Okay. Now, by viewing the shear force diagram, right? If we are going to focus on shear stress, is equal to VQ over IT, right? There are two points of interest, right? There are 2 points of interest. One point of interest, by just looking at the shear force, one point of interest is X is equal to what? 0.8. The other point of interest is X is equal to 3.2 for now. Why? Because over here, you have what? You have V is equal to 80 times 10 to the power 3. And you have V over here, which is equal to what? Minus 40 times 10 to the power 3. So there are 2 points of interest. X is equal to 0.8, X is equal to 3.2 by just viewing the what? Shear force diagram. But we know that this structure is also loaded due to what? Bending moment. Yes or no? So the next thing that we will sketch is our bending moment diagram. Okay, so our bending moment diagram, I'm going to draw a scale of 48, okay, 44, 40, 36, 32, 28, 24, 20, 16, 12, 8, 4, 0. Do I have enough space? Oh, thank God. Then I'm going to have minus 4, minus 8, minus 12, and minus 16. Okay. I'm going to push this longer. Oh, undo. So this is where we sketch our what? Our, oi. Okay, I'm not going to fight the computer. They win. So next, we are going to sketch our bending moment diagram. Yeah, we're going to sketch our bending moment diagram. So this is moment, right? One thing for sure, if I were to zoom out, both point A and point D will have 0 bending moment, okay? So this will be at 0. And at point D, with a distance of, I don't know why it's doing this, but bear with me, okay? Usually. So this is our X, 0.8, 3.2, 4.0, okay? So we can take the area of the what? area of the shear force diagram to get our what? Bending moment, what? Magnitude. Okay. So over here, you will have what? So over here, you will have, so the point at 0.8 is minus, okay, so it's minus half times by base and times by height. So this is equal to half 0.5 times 0.8 times by 40 is equal to minus 16 times 10 to the power 3 Newton meter. Okay, so it's over here. But is it a straight line or a curve now? Why? Why is it second order? Hey, because the other one is